First, I would have chanted my mo'oku au, but I know I would make a mistake in the middle of it, so I have to. Instead, I'm going to go with this modern, high-tech way of doing it. So my name is Paul Coleman. I'm actually an astrophysicist at the Institute for Astronomy in Hawaii, and I'm currently located at on Oahu. Let's see if I can get this to switch. There. So this is my family tree. You kind of see all the names, but that's me down here somewhere. This side of the tree is German, Portuguese, Irish. This side of the tree is German, Chinese, Hawaiian. Okay, and in particular, I just wanted to point out one part of it, and that's to zoom in over here on this particular tree. This is the Hawaiians that come from Kohala. Okay, and right here, my great-great-great-great-great-grandfather was Hupak Singh. So I am indeed Chinese. I look very Chinese too. But just like all of us, we're all poi dogs, so we all have so much of everything in us. And the reason I'm pointing this out is not because of Hupak Singh. He's a good story. And he also was one of the guys who ran the sugar mill in Hilo for one of the Kamehamehas. Okay. So that connects back to this island in a nice way. But it's because he married Mele Makini, and Mele Makini, you can trace her back, you find out that she's part of the Kalakaua line, okay? And being part of the Kalakaua line means that then you can trace the Kalakaua line back to the Big Bang, okay, through the Kumulipo. Now, I happen to be a cosmology guy. I'm interested in the large-scale structure of the universe as a whole. And so I can go to a conference and I can say, hey, I can trace my genealogy back to the Big Bang, okay? And so this is the sum total of the personal part. Besides one other thing, which I'm going to give you a little bit of perspective. I first visited the summit of Mauna Kea in 1972. How many of you guys were alive then, right? It's great to see the young people really involved because they weren't there from the beginning, right? But they're catching up. I went to my first observing run on the mountain in 1986, okay? So I've seen it go from a place where everything was closed off, you weren't allowed to go up beyond Halepohaku, to the current state that it's in now, where everybody can visit if they want, and preference is given to cultural practitioners. I would also like to point out that my tutu taught English in elementary school. Okay, the twist is she taught it to native Hawaiian speakers. Okay, that doesn't happen anywhere in the world now, right? Nobody teaches English to native Hawaiian speakers. We're talking about speakers who are learning through going to school. And unfortunately, when I was in school, we didn't have any schools where I could go and learn the language or learn the culture. So I'm playing catch up myself, just as we all are. All right. So I just love this picture because it shows the islands. I'll keep trying. And I have this habit of when I get to a joke, I sort of trail off and be quiet, So my students complain about this all the time. So I'll try my best. And by the way, I don't mind if you fall asleep because this is science after all. So unless you're really into it, I won't feel bad. Okay. You're so kind and such a liar. So the reason I like this, I don't care about all the we got this in Maui and in Hilo and Maui, and it's just that it shows the interconnectedness between the islands. Yeah, if you look at these views, you can see that, in fact, the islands are all connected, right? So that's kind of a cool kind of interconnection thing that I like. It also shows that some of the old large volcanoes just sort of went into the ocean, right? And if you go over by Oahu, you see the two huge volcanoes that used to be there that are now the Ko'olau and Waimea, Waianae ranges, yeah? Anyway, so I just like that, so go on. Then I like to show this because this just kind of shows where the evil Empire telescope is going to go, right? Over there on the northern plateau, all right? And also one thing about this picture is by the time that telescope is built, I think 3 of these might possibly be gone, okay? 3 of the telescopes there already. In this picture alone. We're not talking about over there where there's 3 or 4 more that could be gone. But anyway, so don't worry about that. Now let's talk about the TMT and the science that can be done with it. The TMT will be a telescope that observes from where the ultraviolet ends through halfway through the infrared. Okay, so all of the wavelengths that we see with our eyes, that's the visible, that's the colors right there, the spectrum that's colors. And then some of the spectrum that snakes see, right, it's the infrared. Body temperature, they see thermal things. There are many telescopes, some of them only observe in the radio, okay, on Mauna Kea. Some are more dedicated to the infrared rather than the visible, but they all have different wavelength ranges. So TMT is going to be those wavelength ranges. The reason why the TMT wavelength ranges go this way is, imagine this pink thing is a mountain. It's actually how much the atmosphere absorbs radiation. So you can see that, thank goodness, it absorbs all the UV radiation because we would be burned, right? That's stuff that'll fry us. I'd rather touch with my finger. But anyway, my pointer doesn't work, so now I got to use a stick. Anyway, so this mountain here, that tells you how high you got to go in order to detect X-rays, right? So look, you got to go up to 120, kilometers before you can get X-rays. This line across the bottom here is the height of Mauna Kea. So you can see this is why the TMT is looking invisible to halfway through the infrared, right? Because it's still possible to observe stuff there, yeah? And this is why we have radio telescopes. They love, you put them anywhere, right? Radio telescopes can work on, at the beach, right? There's no problem with the atmosphere for a radio telescope. But this kind of just tells you why we go to certain wavelengths. Okay. So the TMT telescope will take advantage of all of this adaptive optics that's been discovered and worked on over the years. In particular here on Mauna Kea, the IFA actually developed most of the modern adaptive optics systems. And so these are just a few examples of where you take a picture and you make it look better by using adaptive optics to try to get rid of some of the atmosphere that's coming through and hitting your telescope. So you can't really see the bottom here. But let me just show you another reason why. Why do we go to 30 meters? Why is it important to make a bigger telescope? Well, this is a picture of the Hubble Deep Field. So that's a picture taken with the space telescope, floating out above our atmosphere, taking pictures. And in particular, if you look at this one galaxy and zoom in on it, this is the best resolution you can do with that picture. Okay, we all kind of know this now, right? We all have cameras where we can look at the picture. We get this, what's called pixelation. I couldn't talk like this 10 years ago because people didn't have their cameras, on their cell phones. But you can now. So that's the best you can do with the current space telescope. Now, when the TMT comes rolling around, you'll be able to do 10 times better. So I want you to know, you decide whether the technology and the benefits are worth the interruption of the kapu, right? But so I'll just give you all the information on the science side, and you can make up your own minds, all right? So this is what the TMT with adaptive optics will be like, and that down there just says that it's about 10 or 12 times better than the current space telescope. And it's going to be about 5 or 6 times better than the new space telescope that they're going to be building. Okay. So it will be, in fact, the most powerful telescope on Earth. And paired with the one in the south, that will mean we'll be able to cover the entire sky to these fantastic levels. And do pretty good pictures, too. So here's another example. Here's M32. I think the one on the end there is, this is data taken with Gemini, I think, and adaptive optics from Gemini. Then this is what it would look like on the new space telescope. And this is the final value of what it would look like on the TMT. By the way, this is 5 times better than this, and this is 5 times better than that. Okay, so clearly it will again be a great place for science. Now, what else happens when you get a big telescope? When you get a big telescope, you're able to look at fainter and fainter things, not just looking at things with better resolution and seeing the details and all that stuff, but you can actually look further away, yeah? So to look further away, I got to talk a little bit about the Big Bang. And you may or may not know about the Big Bang. You know, it's that comedy show that's on TV, right? The Big Bang. That's okay. Those guys, I really empathize with them because that was my group when I was in grad school. It's hard to. We had a Kuthar, we had, you know, it's incredible. It's true. And there was always a Sheldon too. Okay, so the Big Bang, what we think happens is, and this is based on scientific, you know, experimentation, gathering of data, looking in every direction in the sky. We think that the universe started as a small, very compact thing and then exploded. Now, it did all kinds of crazy stuff. I'm not going to talk about any of this crazy stuff. We could talk about it. It's real interesting physics. But the only place where we're going to worry about the universe is right up here. When the universe gets to be, I think the number is 380,000 years old. Because when it gets to be about that old is when you can actually see through the universe. Okay. Before that, imagine this room was filled with smoke, right? I couldn't see anything in this room, and that's because the smoke is absorbing all the radiation, right? When it comes through the room, it gets absorbed on its way to your eyes, and you can't see any further than a little bit in front of your face. That's what that part down here is like. We will never be able to see down here. Okay? Don't care how many telescopes we build, we'll never ever be able to see beyond what's called, this is called the decoupling or reionization epoch, where the dark ages started. Okay? We won't be able to do it. The only way we can see it is if some particle from down here comes through. Okay, then we can. So there's things called neutrinos there around. But no need to worry about that. But the point is, this is the limit to the universe that we'll ever see. Okay? And it turns out that if the TMT works the way it's supposed to work, it'll go right up to that limit. So it'll literally see as much of the universe as is possible to see from Earth. Okay? As is possible to see according to our theories of physics and science. So pretty cool, but okay, so let's turn this to the side because I have a better picture that I like and slide it over a little bit, and this is the better picture. And over here you'll see the Space Telescope, because I actually stole this from a guy at Space Telescope. Actually, the guy at Space Telescope is a native Hawaiian guy who used to be the director of Space Telescope Science Institute. So, of course, he was born and raised in Wisconsin, so he kind of doesn't have any connection to the things we've been talking about today. But, okay, so if you look at the universe in this way, this is the Big Bang over here. Here's the radiation era, and then right here is that decoupling epoch that we will never be able to see beyond. Okay, no way. Because it's like looking into in a smoke-filled room. Okay. The first stars were actually, it's called the Dark Ages, simply because at this point right here is where radiation gets free, and suddenly you can look through this room again. Okay, there's a lot of smoke, but you can look all the way to the other end of the room. Okay, that's decoupling. That means the radiation and the matter have separated, so you can actually look at them. That's called the Dark Ages because there's nothing there giving off energy, right? It's just a bunch of particles, elementary particles, and some photons floating around. Okay, once the photons go by, that's it. Okay. But what happens is, as the universe continues to expand and get colder and colder and colder and bigger and bigger and bigger, eventually stars start to form. Okay, so matter crunches together and becomes stars. And we all know what happens with stars, right? We get radiation from them, temperature, warmth, things like that. So that starts happening at this point in the universe. It's called first stars, right, when the first stars are. You go a little bit further down, you'll actually find the place where the first galaxies form, okay, a little further in time. Not further in time from us, but further in time, meaning as the universe grows older and older. Okay. So first galaxies are actually closer to us than the first stars. Okay. All right, well, because of all those stars and all those galaxies, you're reheating the universe. The universe otherwise starts off as this hot thing and just expands and cools, right? So you would expect it to continue cooling. But suddenly there's stars here that are pumping energy into the system again, and galaxies also. So the universe gets what is called a little jolt of reheating. Okay. Now, the Hubble Space Telescope spent a lot of time, a think, a month's worth of observing, just looking at one spot in the sky, and did what was called the Ultra Deep Field Survey. Okay, the Deep Field Survey is basically that Hubble Deep Field line right here. That's basically how far Earth-based telescopes can look. Okay, the Keck telescope, any of those telescopes, can really only sort of look to here. Okay, but the Hubble Ultra Deep Field Survey points to where the new space telescope will actually be able to look. So the new space telescope will be close to the epoch when the first galaxies were forming, but it won't quite do it either. Okay. Yeah. So this is, by the way, this is the Hubble Deep Field, Ultra Deep Field, and I think it is. I'm pretty sure it is. But if you look at it, it looks just like the nearby universe. There's galaxies, there's weird-looking things, there's spiral galaxies, there's all kinds of stuff that you would see just if you took a picture with a camera outside. Okay. So it doesn't look like much is going on. It would be nice to actually quantify that and figure out what's going on. So that's part of one of the plans or one of the programs. Now, if you replace the Space Telescope with the TMT will be able to go, if everything works correctly, out to the edge of the known universe. Okay, that's incredibly cool because, of course, we'll be able to see the epoch where the first stars start to form. We'll be able to see the way the elements actually work. How did they come out? We're all made of star stuff, as we know both from Hawaiian tradition and from our own science tradition. That where did that come from? Well, this is where the stars are first going to be formed, and this is where we can see it with the TMT. I told my mo'oku how and told you how I'm connected to the Big Bang. This is why. TMT, look at this. I get to look at my ancestors, in a serious way. Okay, so here's a bunch of future science possibilities for the TMT. One is extrasolar planets. Everybody's hot for that. The first time we find life on another planet, it's a game changer, right? It literally changes everything we know about the universe. So discovery of new planets, study of the atmospheres, and looking for constituents of life, looking for water, right? Cosmological acceleration. This is something that was seen because of distant supernova, and I'll show a little bit about that later. We look to the edge of the universe, right? Literally the edge of the universe. The first stars and galaxies after the Big Bang. We will also start to look into the mass of the universe, where it is, where's the ordinary matter, where did it end up? Okay, we can look at that. Does that help us? I don't know. Okay, I'm not talking about this. I'm not doing any judgment calls. I'm just talking about the science. So, for example, this is a simulation of what stars forming at a redshift of 10. Redshift of 10 just means very far in the past of the universe. Okay, and you can see this, by the way, is a simulation of the stars, and this is what the simulation would look like with a 30-meter telescope. So easily detectable. Again, this is the ultra deep field, Hubble Ultra Deep Field, and those galaxies. Go back a second. All these galaxies, there's something like 6,000 in the survey. Every one of them, we'd like to be able to take a spectrum of it. We'd like to do a fingerprint, right? That's what a spectrum is. It's a fancy fingerprint of a galaxy, so that we could understand what's going on there. Okay. Well, we can't. Okay. In fact, down here, this orange strip there is what you can do with the Keck telescope. It doesn't go to faint enough galaxies. And then this blue thing here is actually where the Hubble Space Telescope spectroscopy will go. But with the TMT, we can in fact get every single galaxy in that survey. Okay, we can get their fingerprint. We can find out what they are. Are they strange-looking things compared to what galaxies are here, or are they a new kind of galaxy, or are they the same story? All of those things would be very important for a scientist. You can see the formation of giant galaxies. So maybe those are formed by collisions of two other galaxies. So this is a group of simulations. This is actually a real Hubble picture of two galaxies colliding. Okay, we're bound to see a lot more of this as well, because we'll just go back to that epoch, to that time in the universe. And here's just a bunch of showing that these things can be seen as you push it further back in space. So that the last one, it's actually an oxygen 3-line picture. Don't worry about that, just means that it's a special thing that gives off radiation, and it's due to oxygen 3. But it's at a redshift that's very far away, more than half the universe. A redshift of 1 is sort of half the universe's distance. So, and you can still, with the TMT, see this. So we can observe colliding galaxies and see whether or not they make new galaxies. There's this cosmic web, which you can't see the TMT down there at the bottom, but the TMT will look at bright sources far away as those bright sources shine through the cosmic web of material between us and them. We'll be able to look at spectra of those sources and see absorption features where, in fact, there's stuff, okay, that's been absorbed because you're hitting material on the way to your eyes. So this is an input spectrum. This is what the current 8-meter telescopes like Gemini and Subaru would be able to see. And then down here, which you can't see, it turns out just looks exactly like this one up here. So with a little bit more noise throughout the spectrum, but you can actually be able to completely get back all of the information for these objects very far away and running through this cosmic web, which would be great because what I do is work on the cosmic web. Okay, that's my. Speaking of spiders, I'm the web guy. I mean, if I could find more details about this web, that's what I'm in the game for. Okay, doing the TMT will connect you with the very far distant part of the universe to the current. Okay, because you can use the TMT to step from here all the way out to the edge, out to where the radiation decouples from the matter. Okay, so a complete continuous picture. Whereas now we only really sort of have the stuff near us. We only have the nearby universe, and we have this incredible amount of radiation that broke free. Okay, this is called the microwave background. Okay, and since that broke free, it's actually gotten longer wavelength until it's now in the microwaves and lower energy. So we can see what the universe may have looked back then, but in fact now with the TMT we can actually step through and maybe get to that end picture as well. Just depends on whether the sensitivities work out. Protoplanetary disks. I told Mike I'd have the slide of him. But the point is, with current resolutions of telescopes on Earth, we can only do sort of this kind of quality out to sort of the radius that Pluto goes around the sun. But with the TMT, you'll be able to do another factor of 10, so much closer in. You'll be able to look for these protoplanets that are much closer into the central stars. Exploring the other solar systems, well, I wrote yesterday there were nearly 2,000 planets found around other stars. Yeah, I mean, I looked it up, went on the web. There's a website that keeps track of how many planets are being found. And yesterday there were almost 2,000. Contrast that to when I was a little kid. When I was a little kid, there were only 9 planets in the whole universe, right? Our solar system. But now there's at least 2,000 of them, and probably a lot more. Probably there's planets just about around every star. And as you go over there on the side, you can't really see it. Maybe I'll push this around. I can do that. But most planetary systems are completely different than ours. Okay, they're the ones we see so far, and we're kind of stuck with it, are the things that have like super Jupiters. Okay, so they're very big Jupiters. And direct images have been done sort of on, I guess, 19 or 20 planets, and that's it, direct imaging. But with the TMT, I think it's the next slide. With the TMT, you'll actually be able to do hundreds of them. You'll be able to do planets, reasonably sized planets, out to sort of Virgo, the Virgo cluster, which is the nearest big cluster of galaxies to the Earth. This is also another Mike Liu thing. He's into so many cool planet things. This is a picture, you can't really see it. There's a brown dwarf orbiting this star. Now, brown dwarfs are very faint, and so we need to have the extra collecting area of the TMT to be able to go and see more brown dwarfs and perhaps even closer to stars. 30-meter telescope is required. Just skip this part. Anyway, this one, unfortunately, down at the bottom there is where the supernova is, and let's pretend that I'm gonna blow it up a little bit here. See that bright star down there? That's actually a supernova, and no, we don't want to adjust the keystone, please. Now I'll never get that out of there. Oh. Yeah, see, I would just keep pushing buttons. See, I just tell you, it's the force. We use the force. But the point about showing that was that supernova was as bright as this whole galaxy, right? So they're cool things to find, and with the TMT, we should be able to find them, just like we did with the Hubble Space Telescope, just like we how we have done follow-ups with the Keck and Subaru. And we'll be able to see them even further in space and time. Okay, so what they do is, unfortunately, for me, because I like things to be easy, it looks like those supernovae that have been looked at in the past have shown that the universe is actually speeding up. Okay, so I go, I was a physicist, what's going on? You got little rocket packs on all the galaxies or something? I don't know. But somehow the universe is not just exploding and slowing down like we know an explosion would do, or coasting at the same speed, but it's actually speeding up. So TMT will be able to populate this area of this plot a lot more, and we'll be able to really nail down this. It'll be kind of scary because there were Nobel Prizes given for this theory, and if we find that it's wrong, they got to give the money back or something? Something. Okay, another thing that all of that supernova stuff has done is led us to believe or think that perhaps there's a huge amount of stuff that we just don't know about. We just don't know about dark matter, stuff that doesn't give off any kind of radiation that we can detect, and another thing called dark energy. Don't know anything about it. Hopefully, with some smart experiments on the TMT, we'll be able to get some idea about these two things. And they're the predominant, according to current theories, they're the predominant parts of the universe. Dark matter and dark energy. And the rest, us, stars, stuff like that, is just like this sliver of the universe. Not much at all to it. So hopefully TMT will help to shed some light on this. And I just put side by side the TMT and JWST, the James Webb Space Telescope, the new version that's going to be built and sent up in some time. The TMT will be 25 times more sensitive than the Webb. It has better optical sensitivity and higher spectral resolution. It also is has much better spatial resolution than the JWST. I said like about a factor of 5. The JWST has some things going for it too, but I'm just ignoring it for. Look at that. But they are supposed to be pretty complementary instruments. The thing that I think sells the TMT to me more than the James Webb Telescope is the TMT is flexible and upgradable. If something breaks on it, we drive up the mountain and we fix it. Okay? If something breaks on the Webb telescope, it's broken forever. Because the Webb telescope is going to be very, very far away from the Earth. It's going to be further than the distance to the moon. Okay? So I think this is a huge gamble, this one, compared to the TMT, which I think is a something that will give us results and something we can fix right away if something breaks. And just to show you that, here's what the TMT sort of looks like, or one of the models of it. Oh, now he's going to mess with my... Just kidding. Now, see, the next slide, it's going to be on the other side. So, okay, light comes in, hits this mirror here, bounces up and hits this second mirror here, this secondary reflector, bounces back down to another mirror that just sort of aims it, okay? So light coming down here gets aimed to here, 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 any of these places where you can put detectors. So it's not just like a camera where you take a picture and it registers on some chip, right? This is something where you can actually send this to different instruments. And you can build instruments. So in fact, the current slate of instruments is all these things over here, and they all are addressing certain values, certain kinds of problems. But as the telescope runs, what will happen is people will say, oh, wouldn't it be nice if we had this? And they'll go out and build it, okay? And they'll build it so that it fits in one of those slots, and they'll go and they'll use it. Okay, so this telescope over the, say, 2033, assuming there's no extension of the lease and assuming it works at all, will have, you know, many, many different iterations of instruments built for it. Okay. So here's a, let's see if I can get this to work. There, historical alert. I only have a few bells and whistles, so I have to be happy when they work. So this is just something you should remember or think about. When they were building the Hubble Space Telescope, they had a certain list of things that they wanted it to be able to do. Okay, much like I've just talked to you about some of the things that we think the 30-meter will be able to do. So the previous director of Space Telescope wrote this list of 10 things that he felt were the top things that the Space Telescope was able to do during its lifetime. Okay, the first was to see the start of creation of galaxies, the acceleration of the universe, that the supernova showed that the universe seemed to be speeding up, the distance scale measurement of the Hubble constant, okay, big important thing, they got it down to like 0.67 or something like that. Giant black holes in galaxies were seen, emission lines in active galaxies were observed up close and you could watch them change. Intergalactic medium, interstellar medium chemistry, these are all things that have been seen and worked on. Gamma ray burst sources, protoplanetary disks, and extrasolar planets. All these 10 great things. But I should warn you or remind you or tell you that in fact only 5 of them were on the original list. Okay? So no matter what I said to you tonight, if the TMT is up and running, if we can find a way to continue this, if so, the TMT will also completely change. You know, the things that we will discover we'll just have no clue, you know. Who would have thought that the universe was actually accelerating, like there's some guy, you know, pressing on the gas, right? But that's something that came from Space Telescope work. And who knows what the TMT will also bring. So just remember, if this is the Big Bang, these are density fluctuations, recombination, etc. This is where the TMT can look in the universe, right up to the point where we can't look any further. Okay. So, thank you so much.